Welcome, Ishik Boys High School. And a special hello to Mr. Jager's amazing physics class.
Hey everyone.
We are so thrilled to have you join us today for a brand new deep dive.
Welcome to For the Love of Physics. We are Mr. Jager's assistant, joining you for this deep dive.
That's right. And today, we're diving into the fascinating world of lenses.
Ah, lenses.
Yeah, you know those incredible transparent objects that bend light to create images.
Right.
We're going to explore how they work, the different types you see every day, and how they're used in, well, everything from your own eyes to amazing scientific instruments.
Wow, okay.
Our mission today is really to make sense of how lenses help us see the world in completely new ways. And we want to connect it directly to what you're learning in class. Okay, let's unpack this.
Sounds good. It's truly fascinating, isn't it? How fundamental this topic is to, well, how we see everything around us.
Totally.
So when we talk about light bending, what's really unique about how lenses do it compared to, say, just a flat window pane?
That's a great question, actually. Because it all starts with something called refraction.
Refraction, okay.
You know how light bends when it passes from one material to another, like from air into glass?
Uh-huh.
That bending is refraction. Now, with a flat pane of glass, light bends when it goes in, and then it bends again when it comes out.
Right, sort of cancels out.
Well, not exactly cancels, but because the surfaces are parallel, the light rays end up parallel again, just kind of shifted sideways a little bit.
Okay, so it takes a little sidestep but keeps going in the same basic direction. But if the surface is curved, that changes things, right?
Right. Here's where it gets really interesting. See, mirrors reflect light, but lenses use refraction to bend it. And because the surface is curved, the light bends differently at every single point on that curve.
Oh, I see. It's not the same bend everywhere.
Exactly. This varying bend is the secret sauce. It's how lenses can take light rays and precisely redirect them to form an image. A flat pane just can't do that.
And that precision, that control over light, that's why lenses are just everywhere.
Literally everywhere.
In your phone camera, obviously, but also giant telescopes, microscopes.
And even the front of your own eyeball. Your cornea acts like a lens, focusing light onto your retina.
Amazing when you stop and think about it.
It really is.
Yeah.
Okay, so let's meet the two main types of lenses you'll probably encounter most often. First up, converging lenses.
Converging, like bringing things together.
Exactly. These lenses are generally thicker in the middle than they are at their edges.
Okay, thicker middle. Got it.
And because of that shape, they bend parallel light rays inward. They make them come together or converge at a single point.
Ah, okay. Like focusing sunlight with a
magnifying glass. Perfect example. That's a classic converging lens. It brings light together.
Okay, makes sense.
Yep.
So what's the other type?
The other main type is a diverging lens.
Diverging, so spreading out.
Yep. These are the opposite shape. They're thinner in the middle and thicker at the edges.
Thinner middle, thicker edges.
Right. And they do the opposite job. They bend parallel light rays outward, making them spread apart or diverge.
Oh, like when you look through a peephole in a door, everything looks smaller and further away. Is that a diverging lens?
That's a great example. Yes, the diverging lens spreads the light out, making it seem like it's coming from a smaller object further away.
Cool. Okay. Converging brings light together. Diverging spreads it out.
You got it. Now, just like we talked about with mirrors, lenses have a very special point called the focal point.
Right. The focus point.
For a converging lens, it's the spot where those parallel light rays actually meet after passing through the lens.
Where the light converges. Makes sense.
And for a diverging lens, it's a bit different. It's the point from which the spread out rays appear to originate if you trace them backward.
Ah, so it's like where they look like they're coming from even though they don't actually meet there.
Precisely. Now here's a key idea. Every lens actually has two focal points.
Two? Why two?
Because light can pass through the lens from either direction, right? There's a focal point on each side, and they're usually the same distance from the center of the lens.
Okay, that makes sense. One for each direction.
And that distance from the center of the lens to its focal point, that's called the focal length.
Focal length,
A
right.
really fundamental property of a lens. It tells you how strongly it bends light. Shorter focal length, stronger bend.
And you mentioned the magnifying glass activity, focusing sunlight.
Yeah. You can get a rough idea of a converging lens's focal length that way.
Yeah.
If you focus sunlight onto, say, a piece of paper, careful now, the sharpest, smallest point of light.
Yeah.
The distance from the magnifying glass to that spot, that's roughly its focal length.
Oh, cool. But definitely be careful doing that, right?
Absolutely. Safety first. Please don't focus sunlight onto your skin or anything flammable, and never look directly at the sun through any lens. seriously damaging to your eyes.
Good warning. Okay,
Yeah.
so focal points, focal length.
Yeah.
What about the images they make? You mentioned images earlier.
Right. Another key concept is the difference between real and virtual images.
Real versus virtual.
Yeah.
Okay.
A real image is one that you can actually project onto a screen, like a movie projector shining onto the cinema screen.
You can physically put a screen there and see the image on it.
Exactly. Light rays actually converge at the location of a real image.
Okay, so what's a virtual image then?
A virtual image is one that cannot be projected onto a screen. It's where the light rays appear to come from to your eye, but they don't actually meet there.
Like looking in a regular mirror, my reflection looks like it's behind the glass, but obviously it's not really there.
Perfect analogy. Your reflection in a flat mirror is a classic virtual image.
Got it. So which lenses make which kind of image?
Good question. Here's a key difference. Converging lenses are quite versatile. Depending on how close the object is, they can form both real images and virtual images.
Oh, okay. Depends on the setup.
Right, but diverging lenses, they only produce virtual images, always smaller and upright too.
Ah, okay. Only virtual for diverging. That simplifies things a bit.
It does. Now, to really visualize all this, where an image forms, what it looks like, physicists use a tool called ray diagrams.
Ray diagrams. I think we're doing those in class.
Yeah, they're super useful. Basically, you draw a few specific light rays following simple rules, like a ray parallel to the axis, a ray through the center, and where those rays, or their extensions, intersect after passing through the lens. That shows you where the image is and what it's like, bigger, smaller, upside down.
So it's like a graphical way to predict the outcome.
Exactly. We don't need to go into drawing all the specific cases right now, but the important thing is that these diagrams are based on how light actually behaves. They help us understand the characteristics of the image.
They're like a map for the light rays. Cool.
Precisely. Okay, let's shift gears a bit and talk about where we see these lenses in action. We already mentioned the magnifying glass.
Yeah, the converging lens.
Right, so how does it magnify? When you place an object really close to it specifically, inside its focal point, it creates a magnified virtual image.
A virtual image, right? Because you can't project it. And it looks bigger. But why does it look bigger?
That gets into something called angular size.
Angular size.
Yeah. Think about it. What makes something look big or small to you isn't just its actual size, it's how much is your field of vision it takes up. Its angle.
Okay. Like a car far away looks tiny, but up close it fills your view.
Exactly. The car's actual size didn't change, but its angular size did. A magnifying glass basically increases the angular size of a small object. It makes it seem like it's taking up a larger angle in your vision, just as if you move closer to it.
Oh, I get it. It's tricking your eye into thinking the object is closer or bigger than it is by bending the light.
You've got it. It manipulates the apparent size.
That's actually a really clear way to explain it. And speaking of eyes, lenses are crucial for our vision too, aren't they?
Absolutely fundamental. Our eyes have their own built-in lenses. The cornea, which is the clear front part, does most of the focusing, and then the crystalline lens inside makes fine adjustments.
Working together to focus light onto the retina?
Right, onto the retina at the back of the eye. But sometimes that focusing system isn't quite perfect.
Yeah, like needing glasses.
Exactly. Take nearsightedness or myopia. That happens when the eye focuses the light in front of the retina instead of directly on it.
So distant things look blurry because the focus point is too soon.
Precisely. The eye is converging the light too strongly, or the eyeball is a bit too long.
So how do glasses fix that?
With a diverging lens.
Ah, spreading the light out a bit before it hits the eye's lens.
You got it. The diverging lens spreads the incoming light rays slightly, so that when the eye's lens converges them, they focus perfectly on the retina.
Clever. Okay, so what about farsightedness?
Farsightedness, or hyperopia, is the opposite problem. The eye focuses light behind the retina, often because the eye converges light too weakly or the eyeball is a bit too short.
Meaning nearby objects are blurry?
Usually, yes. Especially close-up things. The focus point is too far back.
So the fix would be a converging lens.
Exactly. A converging lens adds a bit more focusing power, bringing the light rays together sooner so they land right on the retina.
Wow. It's amazing how common eyeglasses and contacts are. Just simple physics principles helping millions, probably billions of people see clearly every single day.
It really is incredible. The impact is huge. Now, simple lenses are great, but what if you want to see things that are incredibly tiny or incredibly far away?
Then you need something more powerful, right?
Right. That's where compound lens systems come in. The idea is to combine multiple lenses together.
Like stacking them up.
Sort of. The clever part is that the image formed by the first lens acts as the object for the second lens.
Oh, okay, so the first lens makes an image and the second lens looks at that image.
Exactly. This lets you achieve much higher magnification or different effects. Think about compound microscopes.
For seeing really, really small stuff, like cells.
Yeah, exactly. They typically use two converging lenses. There's an objective lens really close to the specimen,
The one near the object makes sense.
and an eyepiece, which is the lens you look through.
Okay, two converging lenses, what do?
So the objective lens takes the tiny object and creates a real, enlarged, and inverted image inside the microscope tube.
Inverted, so upside down.
Yep, upside down. Then that real image becomes the object for the eyepiece lens. The eyepiece acts like a magnifying glass for that first image, creating a much larger virtual image that you actually see.
Whoa. So the final image is magnified twice, basically. Once by the objective, once by the eyepiece.
That's the basic idea, yes, leading to really high magnification.
And it's still upside down compared to the original thing?
It is. That's a little quirk of most compound microscopes. What you see is inverted.
Huh. Good to know. Are there limits, though? Can you just keep adding lenses and see anything?
Ah, good question. There are limits, especially with visible light. You generally can't see details smaller than about half the wavelength of the light you're using. So individual atoms. Too small for a standard light microscope?
Right, you need different techniques for that, like electron microscopes.
Exactly. Okay, so that's the very small. What about the very far? Refracting telescopes.
For looking at stars and planets.
Right. They also often use two converging lenses, similar in principle to the microscope, but designed differently. There's a large objective lens at the front. Its job is to gather as much light as possible from a distant, faint object.
Bigger lens means more light gathering.
You got it. This objective lens forms a small, real, inverted image of the distant object inside the telescope.
Small, but isn't the point to see it bigger?
Yes, but first you collect the light and form an image. Then, just like the microscope, there's an eyepiece. The eyepiece acts like a magnifying glass for that small, real image formed by the objective.
Ah, so the eyepiece magnifies the image that the objective lens created.
Exactly. It lets you examine that image in detail, making the distant object appear much larger, or at least letting you see details you couldn't otherwise.
So microscope makes tiny things look big, telescope makes far things look detailed and closer, both using combinations of lenses.
That's a great summary. Now, we mentioned ray diagrams are great for visualizing,
Yeah, the graphical method.
but physics also gives us equations for getting precise answers. Numbers.
Ah, the math part.
Just conceptually, though. No calculations today, promise. One key equation is the thin lens equation.
Thin lens equation, okay?
It's a simple formula that connects three things. The distance of the object from the lens,
Okay, object distance.
the distance of the image from the lens,
Image distance.
and the focal length of the lens.
Object distance, image distance, focal length. All connected.
Exactly. It lets you calculate precisely where an image will form if you know the other two things. It works best for lenses that are, well, thin compared to these distances.
And I bet there are rules for signs, like plus or minus.
You guessed it. There are sign conventions. Rules for whether you use a plus or minus sign for each distance and the focal length.
And those signs tell you important stuff.
They do. The signs tell you if the image is real or virtual, if it's upright or inverted, and whether the lens itself is converging or diverging. It's all encoded in the signs.
Very efficient. So you don't just get the distance, you get the type of image too.
Exactly. And alongside that, there's the magnification equation.
To tell you how much bigger or smaller it is?
Precisely. It calculates the ratio of the image size to the object size. And again, the sign tells you if the image is upright or inverted relative to the object.
Makes sense. Equations give you the hard numbers that the ray diagrams sort of sketch out.
That's a perfect way to put it. But remember, everyone, especially Mr. Jager's class, for this deep dive, we're just understanding what these equations do and why they're useful. Don't worry about the calculations right now.
Yeah, Mr. Jager will walk you through all the practice problems and calculations in class. We're just setting the stage.
Exactly. So let's try and wrap this up. We've journeyed through the really amazing world of lenses today.
We definitely covered a lot.
We saw how they bend light using refraction, the big difference between converging lenses that bring light together and diverging lenses that spread it out.
And focal points and focal length, super important properties.
Absolutely. We touched on real images you can project versus virtual images you can only see.
And how converging lenses can make both, but diverging only make virtual ones.
Right. And we saw how these ideas come alive in things like magnifying glasses, the glasses or contacts many of us wear.
Yeah, correcting nearsightedness and farsightedness.
Oh, and in powerful tools like microscopes showing us the micro world and telescopes revealing the cosmos, lenses are truly everywhere, shaping how we perceive reality.
They really do change how we see everything.
They absolutely do. Okay, so for you, our amazing listeners, here's a little something to think about, a reflection question.
All right, let's hear it.
Think about your daily life. Can you spot another object or situation, maybe one we didn't mention, where lenses are at work, helping you see or do something?
Yeah, good question. Beyond cameras and glasses.
And if you identify one, think about what type of lens it might be using, converging or diverging, and how that affects what you see or what the device does.
Give it some thought. You might be surprised where they pop up.
Stay in contact with your physics teacher. Stay creative.